Hello. In this video, we'll be showing how to get a high performance and scientific computing account on at Isaac, the supercomputer cluster at the University of Tennessee, Knoxville. We'll start with a badly spelled search, but from this link. Note that Isaac Legacy will be decommissioned soon, so we're only going to be covering Isaac Next Gen here. Then, if you don't have an account already, you can head on over and request an account. Provide your net ID and password here, and you'll get an email that should guide you through what to do and an email confirmation saying your account was created. And there, the dual authentication and things like that should be set up. If not, or you have some special concerns about your account or process along the way, you can go down here and see the overview and available resources, academic resources, navigating the user portal, requesting an account, and lots of detailed information can be found here. So in requesting an account, for example, there is a section for non-UT researchers. So you can use this to get collaborators from outside the university to have a net ID associated with them so that they can begin using the cluster as well if need be, or if there's a visiting scholar, for example. Now, on the top is a very helpful button. If this still doesn't satisfy some requirement that you have or some concern that you have, you can submit a service request here. When you click that, you'll see over here on the right-hand side, let me get rid of this. See over here on the right-hand side, you can submit a request. When you do this, you'll see you'll have to sign in. You'll get a duo push. And then here you can see all of these different things that you can ask or provide a request on. So if you have trouble accessing something or there's some problem with your account, you can always use this. But coming back in here, if you scroll down now to Isaac Next Generation, you can see there's access and login, available software, and so on. We're going to go ahead and hit the access and login. So here's your host name for a secure connection or SSH. And here's instructions for downloading the Duo two-factor authentication. So if you use this should be done in general for UT resources. You'll need that for accessing most things. So I'm assuming this is done already. Then in your Mac terminal or say in PowerShell for Windows, you can simply type this command, replacing your net ID with your net ID. So we're going to go ahead and do that. Another option is using PuTTY for Windows if you're on Windows. I'm on Windows. I'm going to use PowerShell. So we're going to come here and we see this command. This will pop up. Warning for people logging in, it shouldn't be here. Type in your password. Note that none of the characters showed up. However, the password was still being input. So don't let that fool. I just pushed a dual push to my phone and accepted it. And now I'm here. So I can list everything in the current directory. This is my home directory. I do not advise keeping data here. This is a fairly low storage capacity directory and is not meant to keep or host all of the data from your ongoing projects. For that, we have the new Isaac 24 file system. So we can go here, go to project, and in here, you see that there is a very large number of projects ongoing at UT. If you're associated with one of these, you can access it, and you should be able to store very considerable amount of data here. This is where data after it's been finished and you're no longer using it for projects, ongoing work in a particular project, you can come and store it here. Alternatively, you can get yourself your own data storage locally, say a 4 TB hard drive or something like that. All right, and then this command, change directories back to the home directory. See that I'm back in the same place. Now, a very useful command for executing jobs, you can go to your Scratch directory, and once once in your Scratch directory, you'll be able to access ongoing work. So here's a video demo where I can show how to use the Quantum Espresso DFT code as an example to run while you're doing for various jobs that you might be doing. Now, if you like, I'm going to submit this quickly. So I'm going to VI into this slurm.sh, which is my job script submission file. We don't want to run anything on the login node because as the login node is usually used for very light file editing or writing small scripts, that kind of thing. It's not used for heavy data transfer. It's also not used for actually running jobs on the login node itself, as that will adversely affect a lot of the things that are going on with other people using this node. So we have a job script to submit larger codes to the compute nodes. So here are the SBatch, the Slurm tags that will dictate to the compute cluster how to perform your job. So I'll give you a quick rundown on each of these. Notice all of them have the SBatch first. We start with a bash interpreter at the top here. And move my mouse out of the way. This -J is the job name that you'll see displayed when you want to check and see how your job is doing, whether it's run, why it hasn't run, whether it's completed, and things like that. So -J is job name. So for this case, I have demonstration. SBatch-E is where to put errors that come back from the compute nodes. So for example, if we hit our stack limit because too many tasks were submitted simultaneously and the job is killed because of that, the error will be written to this .e file. That's very useful for showing which nodes had which problem and how you might be able to rectify it. -O is the output. So this is output from the code itself that might have been written to your screen. So with Quantum Espresso, for example, as you'll see, there's not a lot written here. Most of it is relegated to the output files. Here is the ACF account you're using. ACF-UTK0099 is a general use one that allows you to use the open campus nodes that are available for anyone to use. Another one, if this one doesn't work, is 11. These two both access these nodes. 99 usually has a little bit faster queue times, but I've run into issues in the past with some people not being able to use it. But here, nodes is nodes, how many nodes you're asking for. In this case, we'll just ask for one. This is a fairly simple, just example job. So the tasks per node, I want to ask for the whole node. So I'm going to ask for 48 tasks per node, and I'm going to say the total number of tasks is 48. Partition is which group of nodes are you going to use? So here we just want the open campus nodes, and there's also things like campus long or campus GPU that you can change this to. A lot of those details can be found here. So while I'm here, let's just scroll on down in Isaac Next Gen. And you can see what kind of file systems are available, what's available for data transfer, for system overview. We come down here to running jobs. We can see here what kind of quality of service and what valid partitions are available. So this is a very useful resource for that. Since all of that is there, I'm going to continue. So the QoS, or the quality of service, we're going to choose campus. And for the time, we can run up to 24 hours, but we don't need that long, so we're just going to run for one. Ostensibly, the queuing time, if you ask for more queuing time, it will take longer for your job to queue because other people will be asking for shorter times, and the queue policy will cause your job to take a little bit more time, so you don't steal the node for a much longer time when other people would use it. Then we echo the environment variable for Slurm job node list. This will give all of the nodes and the tasks associated with those nodes. what this will allow you to do is check and see which nodes you submitted your job on. So if you find there's some kind of problem on the compute nodes themselves, you can use this when you submit your HPSC request, like I showed earlier. And you can include the exact node numbers, and it will help them narrow down what kind of mistake is happening, whether it's on your end or on the compute nodes, if there's a problem there. So it's a very useful thing to have. Here I unload Anaconda 3 because my bash profile is set up to automatically load it. So I unload it so I can load PE Intel, and which is a prerequisite for Quantum Espresso. Then load the Quantum Espresso itself, the Intel compiled version, and then use srun with this pw.x with the cu.in file, which I have, and I submit it and I write everything to the cu.out file. Then when it finishes, I have echo finish so that I know that everything is good. For example, this will show up in this .o file up here. And the rest of these are not needed right now, so they can actually be deleted. Okay, so we'll write and quit this file. Now we have two files. I'm going to go ahead and submit this. So you can see I've submitted a batch job and I've used the sbatch command. So sbatch is how you submit a job script. So I said sbatch and then this slurm.sh. This was the file I was just on. So now this has let the queue know. So now I can type sq -u for -user and then my net ID, enter. And you can see there are a couple of different jobs running. This is the one I've just submitted. And the reason it's not running right now is because there aren't enough resources, is what it says. The name here is demonstration. And you can see here the campus, which user submitted it, what state it's in, PD is pending, R is running. So with that, while we wait, I will explore what's in these files. And also what is in the Quantum Espresso website that's useful for figuring out how to run DFT a little easier. So here I have an example file with verbose comments so that it's fairly easy to follow. So we have here a calculation type, what kind of total energy convergence and force convergence criteria we have. You can see here the energy stopping for self-consistent field steps in DFT, and I also have the force stopping criteria here. So you can go ahead and copy this file if you want. This file will be made available to anyone who wants to use it. So here we have the out directory. Dot means the one I'm in now. Prefix, the pseudo potential file directory, the right force, right stress, and the verbosity for these. So I like to keep verbosity high so that I can get as much information as possible, especially when I'm not quite sure what I'm looking for in the files. Say if I'm a new user, this lets you see everything available to you, and then you can decide what kinds of things you should be looking for afterward. If you know you don't have, if you know you're going to be creating a lot of files, you can always set this to low to keep the files small. And then we have the energy cutoff for the wave functions in Rydberg's. So here I've chosen IBRAB. It's a tag within Quantum Espresso and set it equal to 0 so that I can specify the crystal cell myself. Here we have n atoms, or the number of atoms. So I have 4 atoms. This is a simple face-centered cubic copper structure so that the job can finish quickly and easily in the time here. We have what kind of occupations you're going to use for the integration technique for the Brilliant zone, the type of smearing. Gaussian is a very safe one. That's why I use it here. It can be used for metals or insulators and the like. It's a great one to choose when you're not quite sure what material you're working with. The value for the magnitude of Gaussian smearing can be submit it here. This is a default value. I'm just showing so that you know, so that you're aware of the tag. Then here we have the conversion threshold for the electrons. So as the electrons are being relaxed, or the charge density is being relaxed, rather, this is the kind of energy criterion that I want the changes to be within before it stops. And then the diagonalization algorithm and so on. A lot of these tags are set to the default values. If you need more information on how to run Quantum Espresso for your specific system, you can visit this website here. So in case you don't have that available to you, just open a new one and go straight into this. So you can just type Quantum Espresso here, and you can see here's the homepage for the Quantum Espresso code. We're waiting a moment while it loads. All right, so here you can go to the users. Here we have documentation of pseudo potentials, which we're going to need, and tutorials as well. If I go to the documentation, input data description here on the left, and then pw.x. You can see here a list of every single possible tag you could use for a pw.x style calculation. There are so many, so as you need, feel free to use them. We're just doing a simple relaxation of a unit cell for FCC copper. So I'll quickly show what that means. Another very useful website is the Material Project Database. Since the cell is already visualized here, I'll just go ahead and open this so that you guys get a sense of what it looks like. So here we have the copper structure. This is what it looks like, except instead of this many atoms, we only have 4 because we're using the minimum, the unit cell for copper. And you can see here they have a lot of data like band structure, density of states, the band gap, density, things like this, these and the lattice parameters. This is all a very, and you can even download the structure itself to start with if you like. Okay, so back to our Quantum Espresso. Here's all of the examples that you can use. So as you go through here, they have a lot of introductions and how to write the file so that you don't end up making a mistake, and so on. So now back to our example. For a relaxation style calculation, we need the control system, electrons and ions, cards. These pieces are called cards and they end with a slash. We have all that. We have the atomic species, its atomic mass number. And now afterward, we need to tell it here what the pseudopotential file is. We already said where it is up at the top here. We have the pseudopotential directory, which is the one that we're currently in. So here is the pseudopotential file that I have already uploaded here. I'll show you that in a minute, and how to make and how to get your own as you need. If you have more atomic species, for example, you wanted to add an atomic species called X into your calculation, you would write X and write the atomic mass number, and then X dot whatever the file name is, right? You can go ahead and do that if you like. And then we have the atomic positions in units of atomic lattice. So here, these are in relative units. So there's an atom at the origin at 0, 0, 0. There's an atom at 0, and then 0.5, 0.5. So this would be an atom in the, excuse me, in the rear face along the 0 in X, but 0.5 in Y and 0.5 in Z, so it would be along the back face of a cube with its corner at the origin. And then here we have one with an atom on the along the left hand face and one on the bottom as well. With periodic boundary conditions as are used in quantum espresso, this is sufficient to completely represent the copper atomic structure. Then we have the K points as 2 by 2 by 2 for sampling the brilliant zone. And we have it set to automatically space them appropriately so that we get a good spread across our unit cell that we're using here. Usually this would be a little bit tighter, but you can get some more of those details as well when you explore the Quantum Espresso website. And then the cell parameters here are shown, and the cell parameters are in units again of atomic lattice spacing. So it's a 1 by 1 by 1 unit cell, or a cube, a perfect cube. A is the lattice parameter. So here we have the lattice parameter of copper set to be 3.593. All right, now we can see our calculation. If I type this SQ-U, you can see it's no longer listed here, and the calculation has correctly finished. So now we can go into this demonstration.o file. You can see it started on this node name with 48 tasks. It loaded PE Intel and the loading requirement. Intel compilers were loaded here. And then that echo finished came in at the end. So we know that it finished correct. We know that it at least ran through the entire file and finished running the Quantum Espresso, or at least it thinks it did. Now we can check the .e file and make sure that there were no errors. Great, it's empty. Okay, now before we move into how to look at the results and get, say, your total energy, we look at this file, and you can see it's very long, 18,000 lines. So this is sort of a difficult thing to get without simply going to the website. So my suggestion is to go to the Quantum Espresso website. Go to the users tab, and they have pseudopotentials. And these are the files needed. So we go on down here. Ready to use pseudopotential tables are here. Okay. And then we can go ahead and click wherever we would like. We have copper. And we can go ahead and choose any of these that we like. I believe I use this one. So if you click here, the entire file is shown here. So I can Control A, Control C to copy, come over here, and for PowerShell with Windows, you can do sudo file, and then press I for insert mode, and then tap with both fingers to paste everything in. Since this would take a considerable amount of time, I'm not going to do it now. I'll save that for the end of the video to show what it would look like. You just need to wait for it to finish pasting, and since there's a lot of data, it takes some time. So with that, we can move to cu.out, the output file that I asked it to make. And you see here a lot of outputs associated with how the calculation is being done. You press Shift G and go to the bottom. You can see job done was printed, which means it did finish successfully. Whether that means it reached the total number of steps you asked it to do, or it actually totally converged and you now have a relaxed copper unit cell. So here at the end, you can see these are the final atomic coordinates after it finished its relaxation. You can see that they're very close to perfect, roughly half an angstrom off at most. And keep in mind, these are not extremely accurate because the calculation parameters shown here are optimized to run in a very quick time so that I can show off the calculation institute. So here we have the different forces on the atoms, the total stress, total force, and here is the total energy. So if we want, every single time the total energy was printed, we can take this exclamation point with some spaces and total energy. We can also see where the Fermi energy, occupation numbers, and what K points are where, what the occupation numbers for those K points are, and the like. So if I want to see the energies quickly, we can do this. And we know from looking at the calculation, every time we see an exclamation point, it's the final total energy printed for that loop. So we can see the calculation. If we scroll up to the top, there's quite a few here. We have negative 381.756, and then sometime later, say at the bottom, negative 381.9047. So the energy is smaller, the energy has converged. Perfect. And you can check the final atomic positions with your structure viewing software of preference. That is these values here. And now I'm going to come back here, Control A, C. Go here. Made insert mode. When I say paste, it's going to warn me it's going to take a while. So I can go here, and as you can see, the paste is going to take quite a while because there are 18,000 lines and we're waiting for it to do it fairly manually. So with that, that concludes the video for how to run a simple quantum espresso calculation and how to use the HPSC. If you'd like to run your own code, you can run it similarly to this. You just need to replace the pw.x line in the slurm file before with the code that you would like to run yourself. All right, thank you for your attention. And since this just finished, one more thing, you can see this new pseudo file will be the pseudo potential that we're going to use. If I want to use the new one, I need to go here and replace this file with new pseudo. And if I want to run a different code, I would simply change this line, srun, and do srun with some other code. Alternatively, the following command also works well. You can do dot slash my executable. And this will execute whatever code is in my executable on the compute nodes. Thank you for your attention. I hope this helped.